let's take a look at lines in 3 space. So we're dealing with 3 dimensions now. We are in, I better choose a better color for that. We are in R3. All right, let's read what this slide has to tell us. Consider a line through a point in 3 space with a direction vector. We find the equation of the line in the same way in 3 space as in 2 space, and this is for each form, vector, parametric, etc. So we have our vector form here. We have our point. So we know a point on the line. We have our parameter, and we have our direction vector. Let's take a look at some of the notation here. We have our generic point P naught here. So P naught or P sub naught. You may have seen this kind of notation and vocabulary before, otherwise maybe not. That's why we're explaining this. So naught kind of sounds like not, but it means the letter. It means the number 0. So often we'll use that to indicate our starting point. So if I move from position 1 to position 2, this would be like position naught, position 1, position 2, and so on. So sometimes we use it to describe things like that. In our case here, we're using it to describe like our kind of like our starting point, our generic point. And so the components of this vector are x naught, y naught, and z naught. We also indicate a specific point on our line somewhere here with P. So let's label that specific point. And its values are x, y, and z. And then we have our direction vector m. And so remember, when we're dealing with our vector form of our equation, we can think of having our given point, and then we travel from that point in the direction of our vector m. And remember, it doesn't matter where the vector is, so we can imagine that we had it here even, and then we moved it over. Let's learn about vectors in 3 space by intuition and examples. So let's think, what do we already know about working with vectors and lines? And let's try to extend it into 3 space, 3-dimensional space. So we're going to have our starting point. We are going to have S is going to be our parameter. So the scalar multiple of our direction vector. S is an element of the real, so I can have any real value assigned to S. So once again, if I have a point and my direction vector, from that point I can travel any multiple of the direction vector. Small multiples if I'm going only a small distance, large for a large distance, negative if I'm going backwards. So these would be negative values of S. So S is less than 0, S is greater than 0, and so on. So we've seen that before. Just a quick refresher of what that looks like. Okay. And let's just describe what we're seeing here. This is the vector equation of a line in 3 space. And I like to use the simpler notation, so we're just going to say R3 rather than writing that out in words. Let's define our parametric equations. So for x is equal to -3 minus 1s, so just minus s. Y is equal to 1 plus s. And z is equal to 8 plus 9s. And I'll try to make sure my s's look like s's and not 5s. Just make sure you're also listening to what I say so we can be clear. How are we going to find 2 specific points on the following lines? Well, oopsie. Try that again. Well, to find specific points, we're going to set the parameter s to different values. Set the parameter parameter s, two different values. And, you know, we could just set it to 5, and then s would be 5, and I wouldn't have to worry about writing it correctly, but maybe we'll try to avoid that just to avoid any confusion. Let's start by allowing our parameter s to have a value of 0. So x, y, z will be equal to -3 minus 0, comma, 1 plus 0, comma, 8 plus 9 times 0. And what are we going to get? We're going to have our specific point located at -3, 1, 8. Let's change our value of s to 1. So our point here, x, y, z, is equal to -3 minus 1, comma, 1 plus 1, comma, 8 plus 9 times 1, which of course will give us the values of -3 minus 1 is -4, 1 plus 1 is 2, and 8 plus 9 is 17. So we have successfully answered the question. We have successfully found two specific points that exist on the following line. So what did we do? Let's just describe our steps. I forget to do that sometimes. You can always remind me. So what did we do? We went from our vector equation to parametric. We chose values for s, and then we found the coordinates of 2 points on our line just by using substitution, setting values for s and plugging them into our parametric equations. All right, cool. Let's move on. In example number 2, a line passes through the points A, which is located at -1, 2, 4, and point B at 3, -3, 5. Write two vector equations for the line and also their corresponding parametric equations. Remember, we've talked before that there is not a vector equation, or sorry, there is not the vector equation of a line. There is a vector equation. There's more than one way to write it. So let's take a look. Vector equation 1. Let's define our point M as equal to AB. So we're going from point A to point B. So we're finding the vector that connects them. And I could sketch this. I'm not going to bother, but if you are interested, you can pause the video and make a quick 3D sketch and see where these points would actually be located. Oops. So let's find those values. Find the difference in x's. So 3 minus -1 is 4. I'm not showing my work now because we've done this a number of times. -3 minus 2 is -5. And 5 minus 4 is 1. This gives us point A. Let's define our vector equation. So R is going to be equal to our point, -1, 2, 4. So we're going to use point A, sorry, to find our vector equation, plus T. Doesn't really matter what letter value you use, whether it's T or S, it's still a parameter. And our direction vector, 4, -5, 1, where T is an element of the real. Let's find our parametric equations. As always, we're just kind of splitting up our vector equation. So x is equal to -1 plus 4t, y is equal to 2 minus 5t, and z is equal to 4 plus 1t. So just t, where t is, an element of the real. Let's find a second vector equation. And we are finding our second vector equation. We can use the same direction vector we used last time. So m AB equals 4, -5, and 1. And just to recall for a little bit, that basically, and I'll demonstrate this in two space, we're just given 2 points. And we're told to define the line that goes between them. We aren't told that we have to use a specific vector. So I went from point A to point B, and I've defined this as my direction vector, but I could have gone from B to A, and that vector would just have the 5, -1, the values of -4, 5, and -1, because it's, AB equals -BA. They're equivalent. So I can use that. I could have used that instead of my direction vector. So let's just write that down as another possibility that we could have done. So I could have had m equal to -4, -4, 5, and -1. Because same thing, I'm still moving along the same line. It's just right now, when when t is positive, I move this way. But if my direction vector was this value, I would have t negative to move this way. So it doesn't matter. It's all relative. Parameter is just some scalar quantity. Also, it can be any multiple of that vector. It all defines the same vector. We're still moving in the same direction. So what if it was shorter? What if I decided my direction vector only went this far? And so maybe my values are something like 2, -5/2 and half. That would be fine. Or we could double it. What if m was like 8, -10, and 2? So, my vector would be something like this instead. Those are all fine. So there's an infinite number of ways of doing this. We use our method of finding, vector AB here, just to have a nice simple direction vector that we can use right away, but it doesn't really matter. Any vector that points in the same direction is fine, or the opposite direction. As long as it points along that line, its magnitude doesn't really matter. So we have a lot of different possibilities there. So other possible values for m, should have wrote them down before I erased them, but we could have had 2, -5/2 half, or we could have had like 8, -10, and 2, whatever. Those are all other possibilities, alternate realities that we could have encountered. And we're going to use point B this time as we define our vector equation. So vector r is going to be point B, which is 3, -3, and 5. And it doesn't matter which point we use because they both lie on the line. Just like when we're used to working with more traditional linear equations in 2 dimensions, it doesn't really matter which point on the line we use in our calculations and stuff. Plus, and because we're creating a separate equation, I'll use s as my parameter. Doesn't really matter. And my direction vector 4, -5, 1. Don't forget to mention that s is an element of the real. Let's find our parametric. So x is equal to 3 plus 4s. Y is equal to -3 minus 5s. Ooh. Really tried to keep those 5s and s's apart. And z is going to be 5 plus 1s, or just plus s. And once again, don't forget to mention, s is an element of the real. Did we answer the question? What were we asked to do? Well, it said write 2 vector equations for the line, and I see 2 vector equations for this line here. And I also see their corresponding parametric equations. So I am personally feeling pretty good about that example, which means we can move on. Our next example 3 is a little bit longer. Let's dive right into it and see what's going on here. Consider the line L. Notice they used a cursive L. I'll often do that in notes. You might notice sometimes when I'm writing that I'll write an L, an L instead of an L, because it's like, is this a 1? Is it an L? Is it a capital I? What is it? So I'll often switch to the cursive for that. And it looks like Miss Spring has also done that in this note, so I appreciate that. Consider the line L. We have the vector equation. 7, 3, 1 is our point, plus our parameter t, comma, 1, negative 1, 3, 1. And so that is our direction vector. So let's just label that here. Our direction vector for line 1 here is negative 1, 3, 1, with each of the lines given below. Determine if the pair of lines is parallel and distinct, perpendicular, coincident, or none of these. So what are these going to look like? Well, parallel is going to be two lines that are not going to intersect. So they'll have the same slope, the same direction vector, so to speak, but they do not start at the same time. Sorry, they don't start at the same position or the same point. And notice it says parallel and distinct. So how would they be parallel and not distinct? Basically, if they were the same line. So if they were coincident, so let's color code this. Parallel and distinct is our situation up here. I'll come back to perpendicular in a moment. I think we know what that means anyway. Coincident is if the lines kind of run in exactly the same location. So we can think of it in terms of our vector equation having the same starting point and having equivalent direction vectors. So this is going to be our coincident, which I will color code a little differently. There is a typo there. Let's type that properly. Coincident. Do we know any words like that? Coincidence, things that happen at the same time. Coincident, being in the same location or being kind of the same thing. Other options were perpendicular. So we know that perpendicular lines meet at 90 degrees. And so therefore we know that their dot product, if they're vectors, is going to be 0. Or none of these. And the none of these option just means like any two random lines that are going to cross at some point. Anything that isn't parallel is going to cross at some point. At least in Euclidean geometry. What is it? Non-Euclidean. If we're dealing with curves, then parallel lines can still intersect. But we don't need to worry about that here. All right, so these are our situations. So let's test. Let's see our actual lines here. Let's work through our example. For A, we're going to start by just looking at the direction vectors. Remember I said if they're parallel or coincident, they need to have like equivalent direction vectors. Direction vector it's kind of like our slope, and lines need to have the same slope or the same direction vector to be either parallel or coincident. So let's just focus on the direction. So the direction vector for our line 2 here, so M2 is equal to 5, 1, 2, and that's a vector. And the direction vector for our first line, M1, is going to be negative 1, 3, and 1. And let's just compare those all. Basically, we're trying to figure out, is it possible that M2 is some scalar multiple of M1? So we'll find that by dividing each of the values and see if we get the same scalar quantity. Because if that was true, there'd be some value k that was true for each. This is just like scaling factor. If you remember back to like grade 10 geometry, when you looked at two triangles and had to determine if one was similar, if they were similar triangles. Same idea here. So let's take a look. Let's just compare. So negative 1 over 5. Is it equal to 3 over 1? Is it equal to 1 over 2? No, we know right away none of these are equal. So therefore, These are not parallel, and they are not collinear or coincident. All right, cool. Let's test for perpendicular. And what is my test to tell if two vectors are perpendicular? Why, we just find the dot product and see if it equals 0. So let's do m1 dot m2 equals, so our first vector m1 was negative 1, 3, 1, dot our second vector 5, 1, 2. Remember, we find the product of our x, y, and z components and then add them, so we're going to have negative 5 plus 3 plus 2. Negative 5 plus 3 plus 2 is in fact 0. Awesome. Dot product equals 0. Therefore, m1 is perpendicular to m2. And that means that, therefore, L1 is perpendicular to L2. Congratulations! We are now using the vector equations of lines, our knowledge about direction vectors, and our knowledge about dot product to predict how lines are going to intersect in three-dimensional space. So that's a pretty powerful tool. That's something we weren't able to do just a few days ago, but now using the pieces that we've learned, they all come together and we can do things like this. Let's take a look at one more example, example B, and notice, we have our vector equation up here for L1, but this equation we're dealing with here for B is going to be parametric. So let's take a look. I want to start by comparing the direction vectors, but in order to do that, I'm going to need to put everything in the same form. So B, we're going to start by looking at the direction vector, but in order to find that, I need to put L3 into vector form. So my vector equation R is going to be my position vector. So 1, 21, 7. Oopsie. Try to keep that tidy. 1, 21, 7 plus our parameter T and the coefficients in front of there. So that T looks funky. I'm not happy with the quality of my writing this evening. So our coefficients were 1, negative 3, and negative 1. And that gives us our direction vector. So our direction vector for line 3, or our M3, is going to be 1, negative 3, and negative 1. Now, just like we did before, we're going to compare the direction vector from our first line and the direction vector from the line that we're considering right now, which was line 3. So M1 had a value of, let's just scroll back and look, negative 1, 3, and 1. And the value for M3 we just found was 1, negative 3, and negative 1. And hey, those are all the same values, just the signs have changed. So let's take a look. Let's try to find that scalar value k. So remember, I'm testing, is it true that M1 is some scalar multiple of M3 and vice versa? So we're going to divide. So let's divide and see if we get the same value every time. 1 over negative 1, is that equal to negative 3 over 3? Is that equal to negative 1 over 1? And yeah, they all simplify to negative 1. So because we get the same value every time, that means that, and in fact, this is our scalar value, so we can say directly that M1 is equal to negative 1 M3, or just M1 is negative M3. And it's a vector, so don't forget I call it a hat sometimes. It's not really a hat, it's an arrow. So don't forget our vector arrow there. So because these are scalar multiples, therefore L1 and L3 are parallel. But there's still another question we need to answer. Are they distinct? So will they run beside each other? Or are they collinear where they run right on top of each other? Let's investigate. So let's ask the question, we'll put it in the note so it's recorded, and then we'll test. But are they distinct? Or coincident? How can we test this? We need to know if they exist, if they have different points. So we need to know if a point, so let's say they are distinct, they'll be something like this. The direction vectors are the same, but if we investigate a point on the line, a point that exists on this line will not exist on this line. So, if we test for a certain value of x, the y values are going to be different. So let's go ahead and actually do that test. Let's consider, do we know any points in any of these lines? Well, yes, we know the point from our first equation, or the vector equation of our first line, 7, 3, 1. So that's going to be our test point here. So let's go ahead and try that. So what is our test? Is a point from L1 on L3. We're going to consider the position vector from our vector equation 7, 3, 1. To do this, we're going to use our parametric equations for line 3. So our first one, we have x equals 1 plus t. We have a known value of x here that we're going to consider. So 7 equals 1 plus t. Rearrange t equals 6. All right, cool. So when t equals 6, our x coordinate, our x value is 7. Let's try our y and z values and see what happens when our parameter is set to 6. So if we get our result back, if I find this point, x, y, and z coordinate when t equals 6, then we'll know. So we just said that the x value is 1 plus t. We subbed in 1 plus 6. We get our 7 back out for our y equals 21 minus 3t equals 21 minus 3 times 6. So 21 minus 18 is 3. Hey, that looks pretty good. I got my 7. And I got my 3. Let's see if we're going to get our 1. So our z component is 7 minus t. So 7 minus t is 6. And that equals 1. That's the value we're looking for. So what does this mean? This means that the point A, 7, 3, 1, also lies on L3. So a point from L1 also exists on L3. That's only possible if the lines are coincident. So let's finish writing that out. I'm running out of room here, but we'll manage somewhere. So we can kind of write it on the side here. So this shows that the point A, 7, 3, 1 also lies on L3, and therefore L1 and L2 are coincident. So they have the same position vector, the same direction vector, and they go through the same point or points on the line. I'll move up here. The watermark might have been covering that. Hopefully you can see the work there and see anything that you missed previously. I'm not going to work through examples C and D, but if you do want to stop and pause the video now and work through those, depending on what time you have available to you, that might not be a bad idea, just to get a feel for it. Let's take a look at our summary here and describe what we have learned so far. So, dealing with equations of lines in 2 space, we can have the vector equation. So our vector is defined by a point on the line and a parameter times our direction vector, where our vector m is equal to a comma b. This is not a unique representation. There are multiple ways we can find a vector equation of a line, not the parametric. We kind of split it up. So x and y are represented by x plus a times t, and y equals b times t, where t is an element of the real. Once again, not a unique representation. We can change the value of our parameter and such as we go. And our scalar or Cartesian equation, where n is equal to our vector n. A normal vector is given by the letters a and b from our standard form, our Cartesian equation. And we proved several slides ago that that is always the case, that relationship between a and b and the normal vector. And this is a unique representation. So this represents, there's only one way of representing a line in this form. Let's talk about R3. The vector equation is very similar. We have a position t times our vector ABC, where our vector m, ABC is our direction vector. Once again, not a unique representation. We can have any point on the line listed here. We can use any multiple of our direction vector. We've seen there's a number of different options there previously. Parametric equation, once again, x, y, and z component, x plus at, y naught plus bt, z naught plus ct, where t is an element of the real. Different ways of writing that. Scalar equation of a line in 3D is not possible. Why not? Well, let's think about it for a moment. So when we're defining here, we have a normal equation. So let's think. We have 2-dimensional space. I have the equation of a line. And I have my vector n that's normal to it. If I know n, there's only one possible direction vector that is going to be parallel to this, or sorry, perpendicular. But why can't I just have ax plus by plus c z plus d equal to 0? Why not? Well, let's think about what's going on here. So we're defining things in terms of their normal. So I'm going to have my 3-dimensional space, x, y, and z. And I'm going to have some line in 3D space. So, you know, that's like over here, and then this one's like over here, you know, whatever. And then I have some line that's perpendicular to it. So I know my vector, my perpendicular vector. So let's say our n here is a, b, c. Does this define a distinct line? Is there only one line in 3-dimensional space that's going to be perpendicular to my normal vector? Well, no. What if I rotated my line about this point? What if I had a new line right here, where I rotated it some more? Or I rotated it some more. Or another one this way, or this way. You'll notice that there's not one unique solution here. There's not just one perpendicular line that's defined by this. Instead, any one of these lines fits, and instead we're kind of forming this, like, you can think of it's kind of like a disc that's forming from all these possible lines. Or it doesn't need to be a disc. It could be like a flat surface. And what do we call a flat surface like that when we're talking about vectors and whatever? Well, a flat surface is just a plane. And so we'll see that this is going to be important later when we talk about planes, but we cannot use it like this to define a single line in 3D space, because it represents an infinite number of lines. It represents a plane, and we'll get into that in our future lessons.